All right, hello everyone, and welcome back to this. We're making a project today. We're doing a project. So today we're going to be starting to combine basically what we were doing in the first two units, which is design and CAD, and we're going to use those together to create a very basic mechanism that could be used on an actual robot, just to sort of keep this whole training curriculum grounded in reality, and to give you something that you can apply as we start to move forward with actual design. So starting off, right, let's get into our task, right? Identifying the task is going to be the first thing that we're going to be doing. And that's the first thing that you're always going to be doing. Knowing what the task is like literally the most important part of your design, because then you can design around that and you can optimize, what you want to be able to do to accomplish that task. And sometimes, like, your task will be different than the tasks that other teams have, right? Your tasks are dictated by strategy. So, like, in the example of the 2020 game, like your task, to play the game could break down into subtasks of, okay, to play this game and to play it well, right, to win is ultimately your task. Um, or usually is your task. Some, robots just like to, look good, which attracts sponsors. But ultimately, the goal is to win. Um, let's be real here. But yeah, so right, your task to win and to play the game will be broken down into subtasks, which are dictated by your strategy. And your strategy is just like, okay, how can we win, right? And I'm not going to get too in depth into this strategy talk, but basically, like picking which things are worth doing, based on how easy they are to do, right? So how can you do them as well as other things, right? So based on how easy they are to do, and also based on what the payoff is. So a good example this year was climbing, right? Like climbing was a little bit harder to do, but the payoff was really good because it's a lot of points. And so that was one of the central pillars of our strategy, and it proved to be very effective in game. Right, so deciding your task is really, really important, and then optimizing what you build to suit that task, right, to be able to accomplish that task is like that's literally what design is, right? Especially the beginning of your design will be all about thinking, okay, basically, very roughly, how can I accomplish this task? Like, if I want to climb, how can I climb? Well, you'd probably want like an elevator with hooks on it, right? That's your most basic concept, and then you get into deciding, what type of elevator, what type of rigging, what motor will we use, how many stages do we want, what height should it be? Should we try to fit under the trench with the elevator? See, there's all sorts of different tasks that you want to be able to think about when you're doing this, and they all come back to the central idea of strategy and how it matters, right? But mainly, right, you want to be identifying your tasks. So go ahead and pause the video and watch this game reveal for the first robotics competition 2017 game, which was called Steamworks. So it had like a steampunk theme, which was kind of questionable, but yeah. So steampunk theme, right? But mainly, you'll notice it's a mass scoring game, right? There's a lot of scoring that goes on, but balls are worth fewer points. So go ahead and watch the game reveal video for that, and you can do that right now. All right, so now that you've done that, right, let's think about what our task is here. And our task, actually, and I will go ahead and go to our task overview, right? We want to design the mechanism that can intake balls in large quantities, right, from the ground, intake them from the ground so that they can be scored by a separate mechanism. So we're not going to worry about this mechanism, right? Typically when you're designing, you're going to be designing in collaboration with your other team members, but usually you're going to be, in this instance, we're going to be designing in a complete vacuum here, right? We don't care what our outtake is. Like in real life, right, we would inform some aspects of our intake to suit our indexer or outtake. Or usually, actually, you want to go from the intake outwards. So like you'd start with the intake, and then like once you had that, you would design an indexer that could fit around. But you'd also design those in conjunction. So I won't get too much into that. But yeah, right, we're just going to be designing in a vacuum today and designing an intake that can intake balls in large quantities through a bumper cutout. Probably through a bumper cutout is what we'll want, although that can change. But it'll be mounted to a drive base and has to be able to intake these balls in large quantities, right? So it doesn't have to be anything crazy, right? Personally, what I'm going to do is just simple frame-mounted spinning rollers, right? So spinning wheels are pretty much how you interact with any sort of piece, right? Because the wheels are easy to spin and control the rotation of, and then the surface of those wheels comes in contact with the balls. And so if you have a spinning wheel here on the top of your robot, like if your robot is from a side view like this, you have a spinning wheel up here, and then your ball is right here, and then you have a spinning wheel also back here, going the opposite direction. If the spinning wheel touches the ball, it'll go up between the two and into your robot, right? Just like that. Right, so it doesn't need to be anything crazy, right? Simple frame-mounted spinning rollers should do the trick, should be quite effective. Although one of the disadvantages of using a frame cutout, right? Because otherwise you'd have to have your rollers come down on some sort of rotary arm, because there is a certain amount of frame that you have to leave closed. Like there's 6 inches that you need to leave closed on either end. So if you make a cutout in the middle of your frame, you're automatically going to have less width for your intake than if you have something that comes up over your bumper, like mounted on a rotary arm or something, right? And the more width is usually the better, but also that's more complex, and really it's not really worth it if you can just drive over balls and intake them much more easily through a bumper cutout, or at least build the mechanism more easily, right? So I think we'll just do frame-mounted spinning rollers, at least I will, powered by a motor, and then we'll do one on top and likely one on the bottom, although you could test whether like a ramp would work, maybe, like so you wouldn't need a second roller, and that could be, discovered in prototyping. But yeah, I'll go ahead and we'll go now to our research portion. Now, first, right, you want to identify your task when you're designing, but the second part you're going to do is look at how people have already completed that task, right? How have people already done it? Because that's really important to know, right? Don't reinvent the wheel. Like your designs are going to be unique, right? Because you built them. And they shouldn't be a carbon copy of everything else. It shouldn't just be copied verbatim. But there's a reason that you see the same concepts applied across many different robots, right? It's because it works. And so you typically want to build something that works, and without having to, build a bunch of feasibility prototypes, right? A bunch of like basic mechanical prototypes just to test if it works, like this here. Without having to build a bunch of these with different types of designs, you can just look at what other people do in action and see, okay, how does this work? Where does it work? Where does it not work? And how can I make it better? And then you will have a good design. Like I don't guarantee it because, I can't, promise that, right? It's not, I don't think that would hold up in court, but yeah. But like, researching existing solutions is super important, and it's a super effective way to have a design that works. And that's, ultimately the task, right, is to have a design that works at doing this thing. So here I have a playlist for 2017 robot reveals, right? So that's going to be a bunch of different robots for this game. It's like 100 videos. You don't need to watch them all. I haven't watched them all, of course. But just go through and pick out a few highlights, like watch 2 or 3, and look at how people solve the intake problem, right? How do you get balls from the ground into your robot in mass quantities? And you're going to see a lot of the same patterns emerge. Now I have 3 main examples here, right? Here we have sort of the style I was talking about earlier, where it's just a frame cutout. You can see that they have the 6 inches of bumper clearance you need on either side, right? You can see that here, where they have an arm extending over their bumper, they can go almost the entire width of the robot, minus the extra part of the bumper. Right, on the robots, there's something called frame perimeter, which is the farthest your robot is allowed to extend outside the bumpers, or inside the bumpers. And so this is like going straight to the edge of frame perimeter. And then it can also come over the frame perimeter while you're in the game. So they could have something theoretically that extends out to the sides, but that would be a little bit silly and it wouldn't really be super useful. But yeah, right, so they're like centered in frame perimeter here and at the edge on either side, and then they have this come over, and then they have a lot of area here this way to intake balls up through. They've got a wheel here and a wheel here, although this may just be a ramp. I'm not sure. And then here you have Team 118's robot. This is Team 254. Here you have Team 118's intake. They just have fixed static rollers, right? You have one roller here and one roller here. And that's just, they spin in opposite directions. And then they intake the balls here. They've got these little plates down here, which I think helps them to just have their balls, come straight into the indexer like that. And I think it also helps them maybe to close off their intake, although I'm not entirely sure. And then you also have a static roller prototype, right? This is a prototype, so you can see it's very basic. But this is something you're going to be building if you want to test feasibility, right? You want to test, does it work? Basically, like at the most basic sense, this is what you do with a prototype. Of course, you can build prototypes to test more specific things, like the spacing between these, right? What material works best for these? Those are all things you would test with a prototype. But this just appears to be a feasibility prototype, like, does this concept work? And you've got one of the balls here, so you see it's a little yellow wiffle ball. And then you've got, these pool noodles here, which they have on PVC rollers. So they're just testing, right? Does this come in? So this is 4646. They made a prototype here. And that's just, a good example of prototyping. And also you can see that it's a common theme with this intake here that's on an actual robot, right? They're built similarly. So go ahead and watch a few of those robot reveals, see what sort of patterns you can pick up, and then come back to me when you finish. So pause the video and do that now. All right, cool. So now that you've done that, and your brain should be full of all sorts of interesting stuff, we'll go ahead and go to our next slide, right? We're going to start this design. And now the workflow for designing is going to be special for you, right? Nobody does it the same way. No two people do it the same way. But personally, how I like to do it, and I think this is sort of applicable to many people, is I start by researching existing designs like we just did and starting to think about potential concepts. Like, the broad strokes would be like you would want spinning rollers, and then like, more sub decisions would be like, do we want it in a bumper cutout or do we want it coming over the bumper? And then you would, make trade-offs like complexity versus simplicity, and like, another drawback or like another more trade-offs, which is like, less reach versus more reach, right? So you always are going to have trade-offs, and deciding that, deciding which ones to do based on those trade-offs are going to be important to your design decisions. But yeah, so research existing designs, right? That's always going to be the first thing. Do a lot of research. In fact, most of the design, like probably half of the design process usually for me, if I'm, just kind of taking my time and doing a design, is going to be research. Because ultimately, if I do that, like if I'm informed, and a lot of times my design doesn't come out looking anything like what I've researched, but it's important to know what's already out there. That way you can inform your decisions strategically when you're making your design. Um, and then ultimately your design will become better because of it if you know what to look for and you know what to learn from all of these existing designs. So then usually I do like a rough 2D graph paper sketch, right? And then here, it details some more like in-depth way I would do the sketching, which is basically just figure out how you're going to get the ball pathing done. So how are you getting the balls from the ground into here? So that'd be a section view, right? Cut down the middle here, what the robot would look like that. So you'd have a roller here and a roller down here, and you'd try to find, the height that you would need here, the compression you'd want on the ball probably wouldn't be much, and the diameter of your roller here. And then you'd need like another one here. You wouldn't find out, anything very specific, like any specific dimension. It doesn't even have to be to scale. Just find the broad strokes of one concept, and then do maybe another concept with, something that comes over the bumper, and see how you could pick the ball up and over the bumper. Something like that, just to sort of see a little bit more in depth the different features of both of these designs. And then you're going to go ahead and look at, you're going to make another sketch as to how you mount this, right? How you mount this system to your robot, which is important to consider. But overall, just, get a better idea and flesh out your concepts that you think of a little bit more, right? Until you have like 2 or 3 good ideas. And then once you have those ideas, right, start to trim them down based on the, things that you're seeing in your concepts, and then you can move on to CAD. So, right after I have my design sort of fleshed out on paper or even in my head, like sometimes I skip the paper step. I know it's sacrilege, but like sometimes you don't really need to use graph paper. It's just if it's just a simple thing, or if you can envision it better than you can on graph paper. But if you have the time, and you usually will, just like take a second and do a simple sketch. Sometimes you'll see things that you wouldn't before. So now go to your CAD, right? Go to CAD software, which we're using Onshape. So you probably go to Onshape and then create CAD of a frame / drive base, right? Your base on which to mount everything. So it's going to be your drive base. We can just use, drive base CAD that we have, and then make like a cutout in it. I'm probably just going to do a bumper cutout here. For this, I'll babysit you guys a little bit more as far as, telling you what I would actually do. But yeah, I'll probably do a bumper cutout on a 6-wheel drive tank drive. Drive base doesn't matter. It's not part of the task. But yeah. And then, you can use a copy of the one in the Onshape team. I think it's this, and right, it's just a West Coast drive. And then you could just create a cutout in the front if that's applicable to your design. It would be to mine. Then you're going to create a CAD base for some sort of side plate, right? It's possible that you could find a common off-the-shelf option. There are like brackets and gussets that you can mount a versaplanetary gearbox to, which in turn can connect to a motor, right? So you have a reduction in that versaplanetary gearbox. It's like, cube shaped, it's like rectangular prism shaped, and then motor mounts to the back. So it's a good form factor, bolts into any sort of plate that you've got there, and it can go directly to a roller, or it can come on a chain to a roller. Right, so you'd create CAD for some sort of side plate, and then you would, have places to mount bearings for your rollers, and then one place to mount your motor gearbox, right, a versaplanetary. So that's how I do it, right, some sort of aluminum side plate, or if you can find a common off-the-shelf option, that would be good too. And then, right, create a CAD mock-up of the ball, so you probably want like a 4-inch sphere. I think that's what it is. It might be, yeah, that looks about 4 inches, 4.5, maybe 4. We'll go with 4. It doesn't need to be perfect. We're not actually going to build this or use it in the game. We'll just assume 4 inches for now, right? So create a CAD mock-up of the ball, and then use that, right? Use the 2D section view drawing from up here to inform roller placement on the side plate there, and then place shaft bearing holes, which are going to be 1.125, so 1 and 1/8 inches outer diameter, in the decided locations on the side plates. So the centers of those holes are going to inform their placement. Right, you'll place the center where you want, and then you'll have to account for roller distance. So if you have a 3-inch roller, right, from the center, it's going to be 1.5 inches down to where you're actually going to touch the ball. So keep that in mind. If you use a 2-inch wheel, it'll be 1 inch down. And then we'll go to the next slide, right? Then you insert those side plates into the main assembly. Make sure there's some way to mount them to the drive base, right? They can either be flat or you can have a bend in them maybe to mount them to the drive base. There's a way, definitely. You'll figure it out. And then make one with the drive base, right? Make an assembly with the drive base and intake assemblies as the full assembly. So then you want to insert bearings, right? Insert hex holes, and then insert a motor and gearbox combination. I'd use a versaplanetary and probably a 775 Pro motor or a Neo 550. Neo 550s are a little bit more expensive, but a lot more compact. So just keep that in mind. If you need compactness, it's fine. But you should be taking cost into account when you're doing this. You don't have to as much here. It's not as complicated of a design. But, take that into account every time you design. We want to give a fundraising team an easy job. But yeah, so some sort of motor, some sort of gearbox, and then constrain these and mate them, right? Put them in the assembly, and then go to, mounting the side plate assembly to the frame, and then you refine some ball pathing, right, using in-context editing, right? So you make, your assembly, then you put the ball where you want it, and then you right-click on the side plate and you say Edit in Context, and that'll allow you to use the ball to inform the placement of the roller. So you go to the center of the bearing hole and you dimension it to the top of the ball, right? You project the ball as a circle onto your sketch on your side plate, and you'd go from edge to edge there, or you'd go from center actually to the edge, and then you just add, you just make it like 2 inches away, or however many inches is the radius of your roller, and then minus however much, compression you want on the roller. So like if you got a 3-inch roller, it's going to be 1.5, probably minus 1/2 of an inch, which is how much squeeze you want on the ball. So that would be like, 1 inch away is going to be the top of your ball from your roller. And then you add chains and sprockets or belts and pulleys to the roller shafts. You don't really need to add chains or belts. You can just add sprockets and pulleys, right? The locations of the presence of chains and pulleys is implied. You can add mock-ups of them in the CAD. It's not necessary though, but it is often nice to have. And then take a step back once you have everything there, right, and review the design from a neutral perspective. Will it work? Can we make it? And what flaws does it have? With this design, there's really only one custom part, and that's the side plate there. So think about how easy it is this to make, right? Like how expensive would this be to make? Probably not super expensive if it's just holes cut in sheet metal. And then can you buy everything that's in the design? Because that is also important. If you can't actually buy stuff, you can't really make it, right? Then use conclusions made here, right, after taking a step back and looking at it from a neutral perspective to inform further iterations and improvements. Right, taking a look at your design without ego is super important, and that allows you to just have a better perspective on it and make better improvements. So don't get too stuck in one lane there. And also, if you're having issues with the in-context editing, right, or actually, never mind. But yeah, so just remember to have your assemblies properly constrained when you're doing stuff like that. That way stuff doesn't move when you don't want it to move. So like that ball, you would probably want to right-click that after putting it where you want and say fix, right? That way it wouldn't move when you dimension to it in your context. But yeah, so use conclusions made here to inform further improvements and developments, right? So we're going to review all of these designs made in a collective meeting. If you're just watching this on YouTube, I'll, create my design, I'll show my design, and I'll do a design review of it so that we can all look at it together. Don't worry about too much about the end goal, right? The fun is in the process. the more you enjoy the process of design, the better and more thought out your designs will become. This is so important to remember because not everything, is a competition, right? Just do this to learn the CAD, to learn the software. This is just a learning exercise. So have fun with it, explore different things, and don't worry too much about a time limit, right? So just set aside some time and sit down and work on it. And don't have any sort of goals, right? Just sit down and work on it. Don't say like, I want to get this done, right? Just sit down and work on it, and you'll find that you actually get stuff done faster. So next time we'll introduce maybe a bit more design complexity with a new project, if we haven't started our off-season project already. But yeah, so we'll do that. And just remember as you're going through this process, right? Remember just to be thinking about like every part of your design should have an intention. Every part of your design should have a reason, right? So if it doesn't really have a purpose, it shouldn't really be there. And then using CAD to embody that design that's in your head, right? Remember that CAD and design are not the same thing, although the line is often blended because design is translated into CAD. Anyway, thank you so much for watching, right? As always, if you have any questions, please let me know. I would love to answer them, and I'll see you all next time. Bye.